thank you very much, Miro, for this very kind invitation. I still remember that I was a co-author of my first paper on MPC, mostly thanks to just helping you to improve the paper a little bit because you were there. Yeah, I think we published in European Journal of Control at that point in time, yeah. So he mentioned that I have been in Dortmund now for 29 years. And in fact, since then I was in the chemical and now biochemical and chemical engineering department. But I'm not a chemical engineer by education. So before I came there, I had at the Fraunhofer Institute done some projects with the chemical industry, but I was not really deep into that. So I had to learn it all. And so I was converted in a way from an electrical engineer to a chemical engineer. And now you can probably wake me up at 2 o'clock in the morning and I can write you down the equations of a CSTR. 40 years ago, it was like Maxwell's equations, but that's long gone. Okay, so maybe that can encourage you to sometimes change paths in your life. And if you do it early enough, then you can still be productive. Okay, so I will talk about multistage optimization, one of the topics we have been working on very intensely in the last 7 years, 8 years. And what I present is almost completely not my work, but the work of my PhD students and of Radu Paulen as a postdoc. I just created the idea and procured the money and had several discussions on it, but you will see that it's all the work of these excellent students. One of them, Shakti, is here, and I will also refer to his work a little bit. And Sankar has helped me to prepare the slides and is also a main contributor to this work. The other main name you will see quite soon. Yeah, so we will talk about robust nonlinear model predictive control. And now the usual slide, why nonlinear model predictive control? Well, if you go to the process industries, then all the companies want optimal utilization of equipment and resources, meeting of quality standards, energy efficiency, resource efficiency, and what is missing? Make money. Okay, so unless you can sort of promise that you will make money, you get nothing done, it's advanced or not. And if you can make money by doing things simple, then they will do it simple. That's sometimes a nuisance for us, but understandable, I think. Okay, but the problem is, and we have a lot of tools in our repertoire that can help to do that. But the big problem in these industries especially is that you have to cope with uncertainties. Okay, so the processes are large. What really happens inside is not always understood well on the fundamental level. They are not sort of clean, like when you build a mechanical electrical device if you do it well. If you don't do it well, then you have also all kinds of problems with friction, stiction, etc. But in chemical engineering, it's sort of inherent to the situation. And you have external influences, and you cannot model things perfectly, and just the double integrator or a second or third order dynamical linear model is not enough to describe the processes. Okay, so one has to do measurements-based control and optimization, so one has to introduce feedback. That's the main essence. Now, I guess you all know about MPC, so nothing special on this slide. So one does a repetitive open loop optimization into the future of your control inputs over the so-called control horizon in order to satisfy some goals for your controlled variable, which is called x of t here, and this is done in an iterative fashion. Now what we have been advocating, and if you may have a look, wrote a survey paper in 2007 in Journal of Process Control, is to use this idea of model predictive control to not just track a reference by the standard linear quadratic control formulation, but you can introduce economic goals or economically motivated goals into the optimization. And that makes it very attractive for industry. It is still something to come. It is not standard practice. But my university, on the occasion of the 50th anniversary of our department, 2 days ago conferred an honorary doctorate to Kostas Pantelidis from PSE Limited and Imperial College. And in his talk on this occasion, he presented that they are actually optimizing a large reactor system at ExxonMobil using this idea of doing online economics optimization using a rigorous large-scale model, and it is nowadays computationally technically feasible. It will not happen everywhere, but when there's enough benefit, it is doable. Now, the problem, of course, is that in NMPC, you do some open loop optimization, which is based on a model. And when the model is not correct, the result will not be correct. So you see here that might lead to constraint violations. It can and will usually lead to a decreased performance. Maybe you're happy, and it also leads to an improved performance, and it can even lead to instability. Okay, so a big issue due to this nature of model predictive control to be an open loop optimization-based technique, the big issue is to cope with the model uncertainties, or plant model mismatch, as it is also called. And this will be in the focus of the talk. I will first introduce the idea of multistage NMPC with an introduction to multistage stochastic optimization in general, and then come to the developments that we have made on multistage NMPC, tube-enhanced multistage NMPC. We'll say a few words on stability and recursive feasibility, but that will be on a qualitative level, and then deal with some extensions. Okay, now, of course, this issue that model predictive control is vulnerable to plant control mismatch was realized very early. And so the earliest work is to minimize the worst case performance over a set of possible models. Okay, min-max, worst case, NMPC. But by nature, you can imagine that that is relatively what we say conservative. Okay, so you have to stay away from the bounds, and you do that once and for all into the future. Okay, so you have the future is uncertain, but you have to come up with one control input that works for all the future trajectories. And that makes it relatively impractical. An improvement on this, or let's say a different idea, which is very close to engineering practice, is tube-based MPC. Okay, so because what you have in any real control solution is that you have layers of feedback controllers that implement what you plan on some higher level. And that's the same idea here. There is a nominal NMPC controller that implements a trajectory, which is optimal in some sense. And then there is the so-called ancillary controller, which keeps the real system under the uncertainty close to the nominal trajectory. Okay, and if you can come up with mathematical descriptions of the uncertainty that you get when you apply this ancillary controller, then you can make sure that you meet the constraints by tightening the constraints on your primary controller. That's the basic idea. That gives up some optimality because the interplay of the two controllers is not optimized in the setup. Okay, and the third idea, which I will present to you now, is multistage NMPC. We started to work on this in 2008. And what makes it different is that there the control moves are computed, taken into account the future feedback. Okay, so that's an idea which is different from the previous ones. Okay, I will explain the details later. I will first explain you the idea of multistage optimization in a more general setting. Okay, so multistage stochastic optimization deals with decision processes which are sequential, which are under uncertainty, and where the uncertainty materializes in stages at certain points. Okay, so for example, you can solve the problem, you want to build and operate a chemical plant. Okay, when you go from now to the end, then you have taken a large number of decisions, up to the point how many shifts you are running tomorrow. But when you look at this decision process, you first decide on where to build the plant, then you decide on the capacity, then you decide, let's say, when you start to operate, how many shifts do you operate, which set points are you using, and then when it comes to the daily operation, you have to decide what to do today, tomorrow. And increasingly, on these levels, you get more information. Okay, so you have a sequence of decisions under uncertainty, but this uncertainty is removed when you progress over time. That's the basic idea. And in order, this you can philosophically set up also for continuous decision spaces, but to make it practical, you need a discretization of the different options, a so-called scenario tree. Okay, I have such a scenario tree here. It comes from another talk, and it is in German, and it does not matter what is on the notes. But it's this idea. Okay, so you want to open a restaurant to build a plant. So before you can do anything on the operational level, you have to decide on the capacity. Will you rent a large space, a small space, a medium-sized space? In which location? Okay, so you take these decisions. And then you start to operate, and you may have more or less demand or more or less visitors to your restaurant. And then you can take decisions. You can hire people or fire people. You can do more advertisement, or you can save the money and put it into your bank account, depending on how the situation evolves. Okay, so you react to this materialization of the realization of the uncertainty by some decisions, and then this process continues day by day, week by week, maybe month by month, depending on how often you can fire and hire people. And after a certain period of time, you may take principal decisions again. So you may continue with the same setup. You may realize that you have rented a place which you will never fill, and therefore better take a smaller one. Or in the worst case here, if you have a small place, few customers, then you may consider to just give up the whole enterprise. Okay, so you have, in the end, you have these different trees of the scenario. Each tree of the scenario is a representation of a sequence of realization of uncertainty and decisions, and it has a final outcome. And what is now done in multi-stage stochastic optimization is that you optimize your decisions, for example, to optimize the average outcome over all these scenarios. And what is in the focus is these first decisions here. Okay, so the issue is which decision to take here, taking into account the existence of the other decisions in the future. Okay, so you explicitly consider that if something happens, I can react to it. Okay, so the decisions in the following stages provide options to react to the realization of the uncertainty, which are called the recourse. And what you're interested in is the so-called here and now decisions, like in NMPC, the next move of your controller. And these here and now decisions are taken considering the option of recourse, the future decisions, explicitly into account. So you must consider everything that can happen in the future, and the decisions are evaluated based usually on an average outcome over all the scenarios, but you can also have two criteria, for example, the risk of your outcomes. Multi- or two-stage optimization is also quite popular in portfolio management, okay, where you think about, I buy something and how do I react if something happens. Now, obviously, this gives rise to a nested decision problem. You may immediately think of dynamic programming where you go this tree backwards, but it becomes difficult to handle. One of the advantages of this multi-stage approach in a discrete setting is that you can decouple the different branches of the scenario tree. Okay, so you can look at the decisions by evolution by evolution. You compute the optimal decisions on each of these paths into the future. But then, of course, you have to take into account that if I'm now at the point now, I don't know what is happening next. Okay, so the decision that I take now has to be one decision because it's based on a certain amount of information that I have. And these are called the non-anticipativity constraints. So in a graphical fashion, you unfold the scenario tree into the parallel evolution along the scenarios, and then you take into account that when you start from the same node with the same information, you have to take one decision. Okay, and you take one decision, use 0, 1 here, and then different realizations of the uncertainty happen. They bring you to a new node, and when you're at this new node, you have to take one decision, U1, 5, 4, 5, 6 here, and they again have to be equal. Okay, so the decisions that are marked with the same color on the right have to be the same, and you can impose this as additional constraints to the optimization, and this makes the optimization problems tractable. So from our experience, more or less, the computational effort grows in continuous settings linearly with the number of scenarios and not exponentially, quadratically, as you may be used from solving large-scale programs. Okay, so we had worked on multi-stage optimization before in a discrete setting in production planning. And the idea was in my mind for quite a while to transfer this to nonlinear model predictive control, but it took a while to get a proposal granted and to get a brilliant PhD student, Sergio Lucia, to work on that. Okay, so the idea is that we represent the MPC problem as a scenario tree. Okay, so at each point in time we have discrete disturbances or discrete uncertainties of the parameters. So we have a set of parameters or a set of uncertainties. And at each point in time we take a decision, and the decisions from each node have to be the same. And then, because we deal with MPC and the strength of MPC is to handle constraints, the constraints must be met for all scenarios. Okay, like in min-max MPC. But the controller in the multistage formulation reacts to the information, or it anticipates the fact that you will gain information at the next state. Okay, so we compute a policy that takes into account all the information that is gained along the scenario tree. Okay, and you can visualize this like the state evolves along a set of scenarios here along this tree, and the controller at each point in time reacts to the past information. Okay, so it evolves on a tree which is delayed by one step. Okay, because here you are at this point, so you have one input. Here you have three possible outcomes according to the different disturbances, and so you have three possible inputs that you take into account, etc. Each stage, the number of input multiplies. Okay, and again, the core is not that you have a scenario tree. The core is not that you take into account the constraints for all branches of the scenario tree. The core is that you have this recourse. You take the future decisions into account based on the future information. So it's a closed loop formulation because the future information is taken into account by means of solving an open loop optimization problem. This has for linear MPC been considered before we started this work, and first the Kaidade did a PhD on using neural nets in NPC, and you may know that there are techniques like bootstrapping where you get a number of neural nets for the same data set, and what he did in his thesis was to apply this multi-stage approach to having a bunch of neural nets that describe the future evolution of your system. And then, as I said, Sergio Lucia started to work on that since 2012. It is an exact formulation of the optimal control problem if the model of the uncertainties is correct. Okay, that's the secret of control theory always. You say something is perfect provided my assumptions are valid. And that's, of course, a strong assumption, but it has to be kept in mind. Now, the problem, as you can see here, is that this scenario tree, if you have, let's say, more than one uncertainty and three realizations, the tree blows up very quickly. And especially if you go along many stages into the future, then it goes up to the number of stages enters to the, so you have the number of possibilities to the power of the number of stages, and that multiplies that. Okay, so therefore, very early we introduced the so-called robust horizon, where you stop branching at a certain point in time. And in the extreme case, you say, okay, I have different possible models for the future, and here I take a decision that should work for all these models in the future, but I assume that here I get the full information about which model is true, and then I take the decisions according to this knowledge. Okay, that's of course an optimistic assumption, but it is one which is effective in the sense that it solves many problems quite nicely. Yeah, I will not spend too much time here, just to remind you, you have the different cost functions for the different scenarios. No, that's for the different stages. And then you have it's for the scenarios. And you have the weights on the scenarios. You can have probabilities that a certain scenario will materialize. And for each scenario, over the prediction horizon, there is a summation of stage costs, and you can also enter terminal costs. And here you have these non-anticipativity constraints that say that the decisions have to be equal if the parent node at which you take this decision is the same for these two decisions. Okay, so you have the cost of the individual scenarios, a weighted sum of the scenarios, a nonlinear predictive model, state and input constraints as usual that have to hold for all the evolutions along the scenario, and the non-anticipativity constraints. Okay, let's see what that can do for us for a practical example. So that's an example that was given to us as a characteristic one by BASF in a EU project quite a while ago. It is a polymerization reactor. In fact, it's on a pilot. The real one is on a pilot scale, but the numbers are scaled up for production scale. it is quite, let's say, standard. You feed a monomer to a reactor, it reacts to the polymer, and you have two means of temperature control. You have a cooling jacket here, and you have an external heat exchanger. So you take some material out of this reactor, you pump it through a heat exchanger, and you feed it back. Yeah. The model is also, if you're from chemical engineering, it is fairly standard. You have mass balances for the different species. You have a reaction which is also taking place in the external heat exchanger. Therefore, there are two reaction speeds here, but they only differ that here the reactor temperature and the temperature of the external heat exchanger is used, and you have the usual equations for heat transfer, for the heat generation by the polymerization reactor. And if you have ever heard about that, polymerizations are chemical reactions that usually produce a lot of heat. So the main problem is to remove this heat so that you keep a constant temperature, because the temperature is crucial for the product quality, for the chain length of the polymers. And you have to feed such that you can still control the process and adapt the temperature control or the temperature set points such that you stay within a certain margin. Okay, we have three control inputs. This is the feed rate, this is the temperature that goes into the external heat jacket, and the temperature that goes into the external heat exchanger. And there are in fact two uncertain parameters, namely here the constant of the reaction speed and the reaction enthalpy. Okay, the control task, the goal of the control is to minimize the batch time, and we assume that these two parameters are uncertain by plus minus 30%. Okay, plus minus 30% for the reaction rate can be realistic. For, let's say, the enthalpy of the reaction, it is a bit on the rough side. What I will do first is I will demonstrate you that it is better to use an economic cost function than a pure tracking cost function. Okay, so in this formulation here, and this is still partially economic, okay, but in this formulation here, we track the temperature set point for the reactor temperature. We penalize in both cases the control moves, and we optimize the amount of polymer that is generated up to a certain point in time. Okay, so this MPK is the amount of polymer in the reactor. Okay, and later we go to the multi-stage case where we then have several scenarios for the uncertain parameters. Okay, so what you see here is the comparison of tracking NMPC and economic NMPC. So in the tracking case, you track the reactor temperature to be exactly on 90 degrees. In the economics optimizing MPC, you have the freedom to adapt the temperature in this window between 88 and 92 degrees Celsius. Okay, and you see that when you exploit this room to maneuver, then the batch is finished quite a bit, 20 minutes maybe, faster than if you just do the optimization and keep the temperature constant. One thing for the future simulations is also important. One constraint is on this adiabatic temperature of the reactor. That means the temperature that the reactor would reach if you have a complete cooling failure. Okay, so your cooling fails, you stop feeding, but then the reaction still is going on because you still have material in the reactor that is able to react, and this temperature is the highest temperature that you get or can get under these circumstances. Okay, and that's limited here also to a certain value, and you see that both controllers keep that value. Okay, now when we have these different scenarios, when we have different speeds of reaction, different amounts of heat produced by the reaction, or we could also use different heat transfer coefficients, then you see that the evolutions of the, and we do standard NMPC with one fixed model that does not know about these parameter uncertainties. So we take the nominal model, but reality is different. Then you see the evolutions of the system here, and you see that the reactor temperature and the adiabatic temperature go above the constraints. And you also see quite a spread of the trajectories of the final times of the reactor. Now, to say, okay, that's what you get if you take your nominal model is a bit unfair, because you can easily see that this will be the situation where you have most of the reaction and the highest heat generation by the reaction. Okay, so what would the control engineer do? Well, he would take this as the nominal model. Okay, so he would make a pessimistic estimate and base, because you want to be on the safe side, base the NMPC on that one. Okay, and then you get this. Okay, you can meet the constraints, not surprisingly, but then you see that the different batches take between 2 and 5 hours. Okay, so you have a big difference if you just apply one model. If you take the right model, you can meet the constraints, but you lose in terms of performance. Now, in multistage NMPC, we used a simple scenario tree that only branches at the first stage. We have 3 uncertainties for the reaction rate, 3 for the heat that is generated, so that gives 9 branches. Okay, and that's what you get in the simulations. You see that all the different trajectories for the different scenarios meet the constraints, both constraints. And you see that before the spread was between 2 and 5 hours, if I took just one nominal model, now the spread of the final times is somewhere between, or let's say the end of the feeding is somewhere between 1 hour and 1.2 hours and 2.4 hours. Okay, and one can do a comparison, and you see that the multi-stage controller gets a much better performance of the process compared to using a single model in nonlinear model predictive control and choosing the model which takes the most pessimistic assumptions. Yeah, of course there is a price. The standard NMPC nowadays with 10 differential equations you can solve quite quickly. The multi-stage controller roughly takes, in this case, 9 times the computation time of the individual controllers. Okay, that's a visualization. And here again you see what is happening. So this is always the time where the control is computed. These are the predictions into the future. And these are the where are they? Here these are the predicted inputs into the future. Okay, and you see the multi-stage controller. Let me stop this for a second. The multi-stage controller computes a set of control inputs for the future and then applies one of them. One can instead also say that I only compute one control input that has to satisfy the constraints for all the scenarios. Okay, so that would be the min-max approach. Apart from that, we optimize the average performance and not the minimal performance. But you only have one of these future control trajectories. You have no recourse that you take into account. And then you see that, again, you have quite a significant performance loss. And there are very simple examples where you cannot even meet the constraints if you only apply one control if you always try to compute one control sequence that satisfies the constraint for all control inputs. If I may go back. You also see that it is not simple in the sense some scenarios go to the lower bound, some scenarios go to the upper bound. Okay, so the control really explores the full range of possibilities. Okay, and something that we also detected, that's another example which I will not explain in detail. What you can see here is that at some point in time a parameter changes abruptly. You can say you have a new feed. Okay, and here we have assumed that we have a controller with a state estimator, and the state estimator can estimate this change of the reaction conditions immediately. Okay, so at this point in time you have the full information. Whereas this is a multi-stage NMPC that does not get this full information. Okay, and you see that even if you get at the point in time when it happens the full information, you go over the constraints because you cannot react fast enough. Whereas the multi-stage controller has taken the possibilities that this or this and something else, 1.2, might happen into account, is not as fast in finishing the batch, you see this here, but it anticipates that this can happen and it meets the constraints. Okay, so anticipation is always a good idea. Now, in many situations, you will not be able to measure all the states. Okay. You have what is called output feedback control. So you need a state estimate. And that's in a cartoon shown here. You have your true state trajectory x of t and you have your estimated state x hat of t, and they differ at the current point in time. When you base your control calculations on this state, then you will get a trajectory that exactly meets the constraints. But as the true state is not where you supposed it to be, you will get a violation of the constraints in your real system. Okay, that's almost inevitable, and it has to be taken into account. So in any practical implementation of some higher order system, you will have the situation that you have to use a state estimator in your control. Okay, and that's the work by Sankar in the recent years, mostly. So the first idea is quite standard in the NMPC literature. So first of all, you do not work with the states, you work with the state estimates. Okay, and these state estimates can be computed if you take, for example, an extended Kalman filter or an unscented Kalman filter. Then you can use the filter equations to compute these predicted states as a function of your system model. So that's always the system model, which could be uncertain, plus the innovations. Okay, so that's the Kalman gain times the innovations. Okay, and by simulating into the future, you can produce the future estimates. Then you need to do two things. You have to bound the error. So for example, you take 2 sigma of your extended Kalman filter, whether that's correct or not. So first of all, you have to say that the true state will be the estimated state plus some error. And if you look at this in a set-based setting, then there is a set of possible errors around the estimate where your future state lies. And then you tighten the constraints, okay? So if you can go up to 110 degrees centigrade and you know that your maximum estimation error is 5 degrees centigrade, then you go to 105. Okay, so that's constraint tightening. Quite simple ideas. But then, of course, as they say, the future is always difficult to predict. So you remember in a Kalman filter or in any of these stochastic filters, you have the noise that comes in the future, and of course you don't know this noise. Now these noises, state noise, measurement noise, they enter through these innovations. Okay, so they are sort of shorthand for everything that you don't know. And then what you have to do when you look into the future is to assume that you have different discrete realizations of these innovations. Okay, so you make some computation, you make some estimates, and then you say, okay, these estimations are, let's say, 0.5, and then I take max, an absolute value, 0.5, and I take minus 0.50, 0.5 as possible discrete representations of my innovations. And then you have to add these uncertainties for each state at each point in time to your scenario tree. Okay, so not only do you have to tighten the constraints, but you get a scenario tree which suddenly becomes much bigger, because at each point in time you have, let's say, 3 different possibilities for these innovations for each state. So the scenario tree quickly becomes quite big. And this triggered the idea of tube-enhanced multistage NMPC. Now, tube-based MPC, as I briefly mentioned already before, is based on the idea that you have, let's say, a nominal trajectory, Z0, Z1, Z2, Z3, etc. And you have the real state trajectory, X0, X1, X2, X3, that evolves in the future. The MPC controller optimizes this nominal trajectory, which constitutes the center of the so-called tube. And then you have the ancillary controller that drives the real state towards this trajectory. Okay, so you have a second controller that removes a part of the uncertainty. Very similar to standard engineering practice. Okay, so you have a valve, you don't know exactly what the throughput through the valve is for a certain opening, and you build a controller using the flow measurement, and you have a controlled valve, and much of the uncertainty has vanished. Okay, that's basically the same engineering idea. And then you have to make sure that these trajectories with an estimate of the uncertainty around the nominal trajectory stays away from the boundaries of your forbidden set. Okay, so again, you have to do constraint tightening. Yeah, so that's the basic idea. And now we extended this to the multistage NMPC setting. So now we have a multistage NMPC controller as the primary controller that has to satisfy tightened constraints. These are these Zs here in the standard case. And here you have now a scenario tree of the Z variables into the future. And then for each evolution along the scenario tree, or each single evolution, you have an ancillary controller, which is also a multi-stage controller that drives the trajectories for these branches towards the trajectories that correspond to the nominal trajectories on these branches. Okay, and then you have also, as a degree of freedom, this initial conditions here that you assume. Now, this can be used to both handle the estimation errors, which blow up the problem, and of which we assume that usually they should not be too large, but also to handle all other kinds of small perturbations. Okay, so what I showed you for this reactor example is that you may vaguely remember that we had lots of parameters in this model. Of course, none of these parameters is really known. And we picked 2, or we could have picked 2, 3, 4 of them, which we thought, okay, they are of primary importance. But in fact, there's uncertainty everywhere. And there are small disturbances in the system. Okay, and now with the combination of tube-based and multi-stage NMPC, we also differentiate in the disturbances. We assume that there are big disturbances, dk. These are the important parameter variations, important possible disturbances, large disturbances. And then we have small disturbances called wk here. Okay, and they are all from a set. And we handle the large magnitude uncertainties by a multi-stage NMPC controller. And because they should not be too many, this is something which is computationally feasible. And then all these small uncertainties are not added to the scenario tree, which would give a huge tree, but they are handled by the tube-based addition to the NMPC controller. Okay, so conceptually, you have a feedback controller that realizes that there is something which was not as planned and drives the trajectories back to one of the branches of the nominal scenario tree. That's computationally much cheaper than handling a large tree. It will cause, if you follow me that the MPC controller is the best possible representation of the situation, then you pay a price because you don't do the optimization taking into account all these possible options. But as these disturbances are small, the effects are also small. Okay, and then the next step is to say the estimation errors are similar to these small disturbances. They are also small, and we take them into account in addition. Okay, so that gives the tube-enhanced multi-stage NMPC. We have a system that is described by a nonlinear differential equation. We have large disturbances dk, small disturbances wk, and we have an output equation with some measurement noise. And all we assume about the estimation scheme is that there is some estimation scheme which is not designed, which is not explicitly simulated, that gives an estimation error within a certain range. Okay, so we can bound the estimation error. And then the estimation error and the small disturbances are handled by the ancillary controller, and the primary controller is initialized with a state estimate which is compatible with these error bounds and which is also compatible with the evolution of the system trajectories over time. And because here you have the estimation error, you have the small disturbances, the constraints for the primary controller have to be tightened such that, so x hat k and has to be in a smaller set by the estimation error, but also the constraints have to be tightened to take care of the additional uncertainty you get from the ancillary control. Okay, so the primary controller acts on these z variables, and it's a classical multi-stage MPC controller. And then the ancillary controller, and that can be an economic and should, in my view, be an economics or economically motivated cost function. And the ancillary controller has a tracking objective. Okay, so it tries to drive the estimated state to the states predicted by the primary controller, and also to track the inputs to make the difference between the real input and the computed primary inputs as small as possible. And you're subject to tightened constraint sets for the inputs that are used here in the primary controller and for the trajectories of the primary controller. Okay, so we have tightened constraints for the primary controller and here a tracking controller. Okay, same example again. Don't need to repeat these equations. Control task is the same, just written a little bit differently here. Smaller realistic uncertainty about the reaction enthalpy. But now we assume that we have only measurements of 2 of the temperatures and that we have an uncertainty in our state equations. Okay, so there are some small perturbations because we cannot control the flows exactly. Something may not be as well. And these can amount to, that's per sampling time. Okay, you might wonder why these units are not derivatives. And same constraints as before. Okay, and here first you see what happens if we do multistage NMPC and we assume certainty equivalence, meaning that we assume the state estimate is the state. We don't care about the state error. Okay, and you see the state estimator works quite well, but there are slight excursions of the bounds by our real state of the system. Now this is the tube enhanced multistage NMPC. You see here that the constraints for the primary controller have been tightened to these, and due to the measurement, due to the small uncertainties, due to the state estimation, you have violation of these constraints. Okay, so this is how the ancillary controller tracks what the primary controller proposes. But due to the tightening of the constraints, these constraint violations do not lead to violations of the original constraints. Okay, and again you see the multi-scenario behavior of the control. Okay, and that's a problem which is not extremely small. Okay, so you have 8 differential states. You have these scenarios, you have the ancillary controller, but you can, with modern soft and hardware, you can solve the problem in 1 second per time step for a sampling rate, which here was 50 seconds, but let's say traditionally would be somewhere between 10 seconds and 1 minute. Yeah, and you also see that the performance is quite good, and that other controllers, a pure tube-based and a pure multi-stage controller, would give rise to constraint violations. Okay, what I did not speak about a lot is that still this tightening of the constraints is a trial and error process. Okay, so in the linear case, you can do exact computations of the sets by which you have to tighten the constraints that guarantee that you meet the performance. Here, because you have this interplay between the disturbances, the state noise, where you already have to make an approximation, for example, some sigma bounds, and then the tuning of the ancillary controller, and that makes it, in the nonlinear case, an iterative process to tighten the constraints. Okay, of course, in control theory, people are very concerned about recursive feasibility and stability. In the linear case, Sergio and others could prove a lot of things. Okay, so you can guarantee robust feasibility under constraints which are the same as you find them in the usual case. In the nonlinear case, the first problem is that you can make a statement, and in the linear case you have the advantage that if you take the extreme realizations of the disturbances and the parameters, you bound the possible states completely. Okay, so you know where you are. In the nonlinear case, you cannot say that in between the extreme trajectories that you have in the tree, there is no other trajectory that goes outside. So you have a much bigger problem. So at the moment, we can only guarantee robust constraint satisfaction if the branches are in the scenario tree. You could apply some reachability analysis to improve that result, but that's computationally costly. Yeah, and otherwise the conditions are the same. Stability is a little bit more tricky, so one can prove input to state practical stability, but there are some complications about the weights in the scenario tree. Okay, so in order to satisfy the convergence to the terminal set, the weights have to satisfy certain assumptions. And the same if you want to have robust asymptotic convergence to the terminal set, you have to introduce, first of all, a stage cost that vanishes when you enter the terminal cost, and you have to assume that there is a dual controller that becomes active when you have reached the terminal set. which is all quite standard to the literature. So one can prove stability to a certain degree, at least, also for these controllers. Now, you may have thought already that if you start to not only do nonlinear model predictive control for a single model, but for a set of models, this becomes computationally costly. And also when you experiment with nonlinear model predictive controllers, it takes a lot of computations, simulations. You may want to do changes, to change your state estimator, to make changes to the model, to make changes to the tuning. So it is advantageous if you have a modular approach where you can implement different parts of the system, simulation, state estimation, optimization in different modules, and then connect them freely. And we also did some, you may want to check in the literature, one of my PhD students did a very nice work on applying nonlinear model predictive control and in the end also multistage to a quite huge reactive distillation column. And he also used this software and could switch from using a simulation to using the real plant in this setting. Okay, so that's about the modularity. And apart from that, it takes state-of-the-art numerical methods. It is based on Casadi and IPOpt mostly, and it provides quite efficient solutions for the solution of NMPC control problems. You are invited to download it from our website and to play with it and help us improve it. And all the results you have seen here are generated using this software. Okay, finally, a few words about extensions. One problem that I have, so far I spoke a lot about plant model mismatch, but that plant model mismatch was of two kinds. One was parameters. So I have a model of given structure and some of the parameters are uncertain. And the other one was disturbances, which I assume to be from a finite set. Now, in reality, you also have so-called structural plant model mismatch. Okay, so you have a true plant that is described by one dynamic model, and you have a plant model that's described by another one, and they may be structurally different. Even the size of the state space may be different. Okay, so what to do then? The first idea that we had was to bound simply the error between the two. Okay, so we assume full measurement of the states, so we can see what the difference between the projected states of the real plant. Okay, so practically those states that we can measure, and we assume that we want to, or let's say we assume that the change of this mismatch over time is bounded. Okay, so we cannot exactly predict what is happening in the future. We can look at the difference from past information between our prediction and the real plant, and then we assume that things grow into the future in terms of this difference only linearly over time. So we have a cone in which the uncertainty evolves. Okay, that's an example with some structural uncertainty. Shakti presented it in his talk 2 days ago or yesterday. Yeah, Wednesday. Yeah, I will not go to the limits. I will just show you one thing. What you see on this slide, and which really triggered some thinking in me, is that ignorance is costly. Okay? Because here you see for this example, which is well known, the difference between using a nonlinear model predictive controller with a true model and what happens if you take this approach. You have a model which is structurally incorrect, you have some parameter errors, you look at what is happening at the current point in time, my predictions are wrong to a certain degree, and I assume that this error cannot grow indefinitely, but it grows linearly over time. And that, you see here, if you use multistage NMPC with this different possible evolutions of the model error into the future, you only get half of the product that you would get with the true model. Okay, so to make errors in modeling is not good. The main problem is that you have to be careful in meeting your constraints. Okay, so the less you know, the more difficult it becomes to compute a trajectory where you meet your constraints in the future. Okay, and therefore the question was, can we do better? And I'm just repeating what Shakti said. in his presentation, the idea is to use a so-called model error model. Okay? The model error model comes from linear control, robust control theory of the 80s, 90s, and it dynamically bounds the uncertainty. Okay, so it represents structural uncertainties, and the idea is to have, for the mismatch between the plant and the model, a dynamic prediction, which is given, and then an uncertainty which is unstructured. Okay, so you can only say here, I have an amplification which is between plus minus 1 if this were scalar. Okay, so the size of this operator is bounded, but the operator itself is not known. But this gives you a feeling for the dynamics. And if you ever worked on robust linear control theory, you know that all the H-infinity stability theorems rely on the fact that you have this shaping of the dynamics along the frequency, otherwise you can do nothing with feedback control. Okay, and from his talk here, you see that when you improve this, when you apply such a model error model, then you can get a lot closer to the possible performance Sn that you could achieve if you had the true model. Okay, so it gives really a significant improvement for such situations. And finally, one more idea, which also comes up very naturally in this multi-stage approach, and this is that so far we have assumed that our scenario tree is given. We have a priori assumed it, we have made some estimates. But of course you can do some parameter estimation online. And you can use this parameter estimation to narrow down the range of your uncertainties. Okay, so along the scenario tree, due to the measurement information, the uncertainty may be reduced. That you can call adaptive multi-stage MPC. And then this reduction here depends on your control input. It depends on how you excite the plant, because that will shape the parameter estimation error. So the idea is to simultaneously choose these control inputs around your prediction horizon to reduce these uncertainties, i.e. to narrow down the scenario tree, and of course to achieve your performance goals. Okay, that's what is called dual control. Now usually in dual control you come up with a cost function which is a weighted sum of two terms. One weights the improvement of your model and the other one is about your performance. In this multi-stage setting we can integrate the two, okay, because we optimize into the future over the cost that you get over your full scenario tree, taking into account that your inputs in the future will reduce the uncertainty along the tree. Okay, so you don't need to come up with some artificial weighting of the two. You can optimize the performance of that you really get with this improved model. Okay, I will not read you to the mathematics, which are not very revealing anyway. That's the example of the paper that Shakti and Rado and Sergio have written on this topic, and it just shows you what you can achieve. Okay, so for a simulation example, here you have what multi-stage control gives you in terms of performance, and when you apply adaptation of your scenario tree to what you get, you already improve. So you narrow down the scenario tree, but you don't compute your inputs according to the information. You just compute them to optimize your performance goal. And then for various more or less conservative implementations of this dual control idea, you get an additional performance gain, which can be also quite high. Okay, so multi-stage NMPC very naturally helps you to formulate a dual control problem and to actually solve it. Of course, there are many issues how to do the parameter estimation, whether you do unfalsified parameter estimation, etc. Okay, so to wrap up, I started by, or I said this also in the middle, the goal of advanced process control should be to optimize the performance of plants in real time. Okay, so to just track a temperature is usually, at least in the process industries, not the main goal. It is now possible to do this type of dynamic online optimization over a finite horizon for realistic plant models online, computationally, and from the basic technology. That's not a problem anymore. but models are never perfect. And when you have ever done a real control implementation, you will have noticed that the modeling error is what really eats up the effort. Okay, so when you do a project, I would say 80% is on modeling, 20% is on controller tuning. Okay, so the less you have to invest into perfect modeling, the better it is for the ability to actually do something. If you go to a company and they say, okay, can you do advanced control of my polymerization reactor? And then you say, yeah, great, give me 3 years for the PhD student who does the model. It becomes difficult. If you say, okay, I can do it in 6 months because I take a standard model and we take care of the not precisely known details in different ways, you're in a much better position. And one needs robustness without sacrificing performance too much. Okay, so the example showed also that ignorance can be quite costly. The strength of multistage MPC is that it includes the future feedback in the optimization, and it can deal with model errors, at least a limited set of model errors, because of this, very efficiently. In the combination with tube-based MPC, you get a very efficient way of handling model errors of different types and still being computationally in a range where it's easy to implement. And it can also handle the estimation errors, which normally should be relatively small. We have an open source software for the efficient implementation of NMPC and especially multistage NMPC, and you're invited to use it and to try it and give us feedback. When I just mention one aspect for the future, then I would say the future, the control community should come back to adaptivity. Okay, in the 1970s, more than 50% of the papers at major control conferences were on adaptive control. There were huge hopes that could be used broadly, and very little of it was really applied for good reasons. But I think if we really want to get better, and given the computational power, also given, honestly, the pressure from the machine learning, artificial intelligence, etc. community who tell us, why don't you use the data, but you always need a PhD student to come up with a rigorous model, and the rigorous model is then wrong anyway. We have to think in the future about adapting our models to the information that we can gain online. The research has somehow reached a certain deadlock, I would not say, but a state where there were severe obstacles that could not be overcome. But maybe in the future there could be ways to reconsider this and come up with robust solutions. Thank you very much for your attention.
I have many questions about each of them questions.
So far, we have not done that. We have sort of the assumption is that by engineering understanding and judgment, you know what are the primary sources of uncertainty. Okay, and of course you can do some simulations to prove that. And then we call all the rest small uncertainties. That may be something that should be verified, of course, from data. But so far at this stage, we make the assumption that we somehow can generate that knowledge. Of course, you can think of many things. You may realize that your set is incomplete and there may be something which is equally important, and then we are back to this issue of adaptivity. Okay, but here we sort the world before we... Thank you very much for inviting me.